Hey, so welcome back, and we're going to do some more LeetCode problems. So today we're going to continue on with this Blind75 list, and we're going to do the binary search questions, a part of it. So if you don't know what this list is, it's essentially just a list of really popular LeetCode problems that a group of FANG engineers came up with these lists of problems organized by basically their problem pattern type. And so today we're doing the binary search problem patterns, which are essentially problems that require you to implement the binary search algorithm in order to solve them in an optimal time complexity. And so if you don't know what binary search is, I'm kind of expecting you to know how to roughly implement the algorithm, or at least know what it is, and just know the concept that essentially allows you to run a search in log of n time, as long as the input or the array or the string or whatever given is already sorted. So that's what allows you to do this in log n time in order to search for that number. And so essentially for this question, what we're given here is a list of numbers that is in a rotated sorted order. And all that really means is that these numbers originally were sorted like this. The thing that happened here was the array was sorted 3 times, or I guess rotated, sorry. And all that means is basically this first number at the end was shifted all the way to the beginning. And so then it looked like 5, 1, 2, 3, 4. And then it was rotated again. So this 4 number was brought to the beginning like so. And then finally rotated one more time and 3 was put here. All right, and so this kind of gives us still a sorted array, which we require for binary search, but they made it a little more challenging for us because it's kind of an increasing order from this point, and then it falls and then starts increasing again, right? So you can see it's this half sorted, and then all the way up to this point sorted, but there's kind of like a gap here in the middle. And the way people typically talk about these types of questions is that there's a cliff. And so essentially the numbers increase and then they fall and then they start increasing again. And so you can imagine it like so. So it goes 3, then 4, then 5, and then it falls down to number 1, and then 2, and then 3. I guess it's actually 4, 5, 6, sorry. All right, and so for this problem, this is the array that's given to us, but what we want to actually do with it is that we want to find the minimum number. And so that's this number here. And what you'll quickly see or come to find is that that number is always going to be at the bottom of this cliff here. And so essentially you can visualize it as it increases until it falls. And at that bottom is going to be our result that we're going to want to return here. All right, and that's pretty much it. So the way you solve this and want to think about it in terms of binary search is that essentially to find this cliff is typically in binary search, you have a left, a middle, and a right pointer. And what you'll find is that when you're looking at the current middle, once you see that the current number that you're looking at, the one that comes before it is actually bigger, then you found your bottom of the cliff. Because essentially when we're looking at the number 1 here, and then the number 6, which comes before it, right? Because it goes 4, 5, 6, then 1. Because this occurrence here is the only point where it goes a bigger number followed by a smaller number, it's no longer in an increasing order, then you found basically your pair that make up this cliff. And so the one on the right, or the smaller one, is the smallest number in this entire array. All right, and that's pretty much the main trick here, is to find that. And then the only other thing is that, okay, how do I know whether I want to shrink my array in the left direction or in the right direction? Because that's part of the binary search algorithm. And essentially all that is that you want to shrink towards the cliff. All right, so towards wherever kind of this dropping point is. And the way you find that is essentially because we have our left, our middle, and our right pointer, we can basically say, okay, is our cliff on this side or is it on this side? And the way you know that is that in this case where we have 3, 4, 5, and then 1, 2, is basically, say we're currently looking at this, and we know this is where our cliff is, right? Because 1's the smallest number. But we know that, okay, if the middle is actually bigger than our right pointer here, then naturally this isn't sorted because it should be increasing, but it's not. At some point it decreased. And so we know the cliff's on this side. How do we know, what if the cliff is actually on this side? And well, say this is actually like 1, 2 here. And so the way we know the cliff is on this side is, well, or actually no, sorry. It would be like, this is a bigger number here, like 6. And then there's some numbers in the middle here. But basically our right pointer is pointing to this and our current pointer's at 5. And so we know the cliff's on this side because we expect that as we go towards the left, the numbers are smallest because it's supposed to be an increasing sorted order. And so if the number on our right pointer is actually bigger than our current pointer, then naturally that cliff has to be on that left-hand side. All right, so if this doesn't make much sense, I think me implementing the algorithm and just chatting with you as we go along will really help. All right, and so essentially, I'll just write out the typical binary search code. So generally you have something like this where you have your left and right pointer. You want to keep going until these overlap and crisscross. And at that point, you want to return whatever's on the left-hand side there, because that'll be the smaller of the two. And so with this, typically you want to calculate whatever's in the middle between those two numbers. And generally you can do it like so. And so, okay, how do we know we found our minimum number in this array? Well, that's going to be at the bottom of the cliff. And how do you know what's at the bottom of the cliff, or if you're there? Well, it's that one case where the number that comes before the current number is actually greater than the current number. And so that means that this is the only point where we're no longer in increasing order. And so let's just go ahead and return this number at this current index. Otherwise, we need to say, okay, is the cliff on the right-hand side or on the left-hand side? And so to do that, we can just say, okay, this is our current number, m, and we want to say, okay, is the left-hand side like less than or equal to this point? And is it also greater than what is on the right-hand side? And so what this means is, say we have like 1, 2, 3, 5, or I guess it would be like 3, 4, 5, 1, 2. And so in this case, our mid's here. We're saying, okay, is the left-hand side less than the right? Yes, it is. So we know that this side's sorted. It's an increasing. And is it actually the midpoint bigger than what's on the right-hand side? And if so, we know that the cliff is in this point because, well, this number is actually bigger than what's on the rightmost side. And so it definitely, at some point, stops increasing, it falls, and it starts increasing again. Otherwise, we know that it's actually, that cliff is on the left-hand side. So cliff is on left side, or the cliff is on the right side. And so if you know it's on the right side, then we want to shrink our search space towards that right side. And so we do it like so. So we say that the left pointer, let's move it up to the midpoint, +1, because we know that the midpoint is not our smallest number, because we checked that here. Otherwise, let's shrink it towards the right side. So let's bring the right pointer down to the midpoint, -1. All right, and success. So this runs in log n time complexity because we're using binary search, but then it runs in O of 1 space complexity because we're just using variables. We're not using any extra data structures that kind of increase with the size of this array. All right, and so let's go ahead and do the second problem. So this one's slightly more challenging, but it's almost the exact same. We still have a sorted array that's been rotated a certain number of times, but instead of finding the smallest number, we want to find the number that's given to us. And so in this case, say if we're trying to find the number 0, we want to return the index where it's located. So 0 is on the 4th index, so we want to search this array and find where in this array that target is. And so we still want to use binary search, and we're still dealing with the case where it's basically increasing, there's a cliff, and it starts increasing again. But we want to find some target that is in this array. And so we still can use all this knowledge of where the cliff is and where it goes increasing, it falls, and then starts increasing again. But we want to kind of shrink it towards wherever the target is, rather than shrinking towards wherever the bottom of the cliff is. And then the only other catch here is that we also have cases where that target isn't actually in this array, and so we want to return -1. And so I think I'm mostly going to show you the code, and we're going to chat and show you where there's these differences between what we previously did and what we did. But I think you already kind of intuitively know a lot of the foundation of what we need to solve this problem. And so what we're going to do is we're going to return -1 if we never find, while kind of iterating through this array, that number we're looking for. And so we're going to say, okay, let's set our pointers to the start and the end of this array, like we always do for these binary search problems. And like always, we want to find our midpoint. This is just all the same code we always write. And well, how do we know we found our target? And well, it's if the current number is that target. And so if that's the case, let's just go ahead and return this index. All right, and so that's just quickly how you'd find the base case or the end case where you found our target. But how do we know which direction we want to shrink towards, right? Do we want to go towards the left side or the right side? And so once again, what we can know is basically what side is like the sorted side without the cliff. All right, and so if we're given the numbers once again, and I'll write these ones out, so 4, 5, 6, 7, then 0, 1, 2. And say if we're trying to find the number 6. And so once again, this is our midpoint, this is our right-hand side, and this is our left-hand side. And so how do we know where the number 6 is? Well, a quick way of finding this out is, okay, this is the current number 7, and on the right side is the number 2. And so we know there's a cliff here. At some point it falls. And we know naturally that 7's only going to be increasing from here, and then it falls and it increases to 2. And so we know there's no way it's going to get to 6. All right, but we know that, well, what about our other side? Could it fall between this range? And so it's between 4 and 7, and well, 6 is definitely going to be between this, so 6 is here. And so basically we can say, okay, if the left-hand side is the one that's like perfectly sorted and 6 is in there, then let's shrink towards it. Otherwise, let's shrink towards the other side. And so this case, like we know 6 is between 4 and 7, and so we want to go towards that side. But let's say instead we're looking for 8. Well, 8 is definitely not between 4 and 7, and so we want to go towards the other side. And basically, you also want to copy paste this and invert the logic for what if the other side, the right-hand side, is the one that's sorted, and the other side, the left-hand side, has the cliff. All right, so let's go ahead and implement this. And I think when I do it, you'll understand a little bit better. And so otherwise, let's say that the sorted half without the cliff is on the left side. And so the way we know this is if the number on the left-hand side is less than or equal to the number that we're currently looking at, right? And so we can say, okay, if our target is between that range, then we want to go towards this left-hand side. So if the target is then between this range, so on the left-hand side is less than or equal to the target, and this is less than our midpoint, then we want to shrink towards the left. So our right pointer is going down towards the middle, -1. Otherwise, it's the opposite case. So then we want to go towards the right-hand side because it's not between that sorted range. And so then we're going to say the left goes up to the midpoint +1. And then finally, we basically want to invert that logic of, okay, then the sorted side is on the right-hand side. And so to do this, we just want to say, okay, then if that number is between the range of the current number at M and then the target is greater than that, but it could be less than or equal to the right-hand side or the right pointer, then okay, then our target falls between that sorted range. So we want to say, okay, then let's move it up to that range. So let's move the left pointer up towards the right-hand side. Otherwise, we want to move our right pointer down towards the left-hand side because it's not in that sorted range. And success. So this also runs in log of n time complexity because we were using binary search. And then the space complexity is also going to be O of 1, just like the last one, because we're not using any extra data structures here. We're just using integers to point to various points and keep track of what the target is and so forth. So yeah, that's the binary search problem type for this Blind75 list. If you want to keep watching my series, I'll be doing the rest of these, and I've done the ones that came before this. So thanks for watching. I hope it helped a little bit, and I hope you kind of caught on to the blueprint code that you typically have to write, and also just recognizing when you want to use binary search or not use it. But yeah, thanks for watching, and good luck with the rest of your algorithms. Awesome. See you later.